Hi everyone and welcome to round 1 of 2018. If you want to gain access to the code that I use in each of my videos, just press the GitHub link in the description and it'll take you to a repository storing all the answers to each of the questions in each of the Olympiads. So without further ado, let's get started with question 1. So for this first question, we're given 3 space-separated integers that represent the number of daytime, evening and weekend minutes spent on calls. And then we're asked to output the total cost given those minutes. So for daytime, the cost is 80 cents per minute after the 100 free minutes. For the evening, it's 70 cents per minute, and the weekends, it's 50 cents per minute. So all we do is we extract the 3 numbers from the input stream, which will be the daytime, evening, and weekend minutes, respectively. Then we initialize our total cost to 0. And then we're going to add our daytime cost. And how we do this is we check first that the daytime is larger than 100. And the daytime minutes is larger than 100. And if it is, then we just subtract the daytime minutes by 100 and multiply it by 80. As in, if this evaluates to true, then we perform this action. Otherwise, we add 0 to total cost, because that means that less than 100 minutes were used, which means the cost was free. And then for the next one, we're adding the evening cost, which is the evening minutes times 70. And then for the third one, we're adding the weekend cost, which is the weekend minutes times 50. Then all we're doing is outputting the total cost. And then just make sure to add C at the end, because I believe this is required. You can see here in the output, they actually put a C at the end of it. So just make sure you do that. End line's not really necessary, but I'll put that there anyways. So that's it for this question. So for this next question, we're supposed to convert text into reverspraket, which is this weird language where for each consonant, you double up the consonant and then add an O in between the consonants. So for example, the ruler, since R is a consonant, we double up R and then place an O in between it. And then vowels, we do nothing, and same thing with spaces. Spaces, you just skip over. And so one important thing to note is that we've got sometimes more than one word in our input. So instead of using the typical cin, we're going to use getLine. So first of all, we declare our input string, and then we use the getLine procedure, and we place the input stream as our first parameter, and then the variable that's going to hold the text as a second parameter. And then before we get into this for loop, I just want to show this isVal function up here. So all it does is it takes in a letter as a constant and as reference, and then it returns whether that letter is a vowel or not by checking whether it's A or E or I or O or U. In some cases, or some people consider Y to be a vowel. I'm not entirely sure about that, but I'm just going to leave it out for now. Anyways, so if any of these evaluates to true, then the whole thing evaluates to true, which means, of course, it's a vowel. So in the for loop, we're just going to cycle through each item in the input string, each index, let's say, in the input string. And if the input string at that position is not a vowel, you can see this exclamation mark, so we're checking that it's not a vowel, and we're also checking that it's not a space. Then what we output to the output stream, or insert into the output stream the character, then an O, and then the character again. So for example, if it was R, it would be R, and then O, and then R again. Otherwise, it just outputs the character, be it a space or a vowel. And that's all for this one. Now let's test with a couple of test cases. We'll start with ruler. You get that weird word. And I just want to test a text that has more than one word. And you can see it works just fine. We get the right output. And maybe this larger one over here. Oh wow, yeah. That's it for this question. So for this last question, we are given as input a number, and we are asked to determine if the number is abundant, deficient, or perfect. And what makes a number deficient, abundant, or perfect is you take the proper divisors of the number, which are all the divisors of a number except itself, and then determine if the sum of all those proper divisors, is either above, in which case above the input number, in which case it's abundant, below, in which case it's deficient, and equal to, in which case it's perfect. So take, for example, 12, which they've given as input here. 12's proper divisors are 1, 2, 3, and 4. And so if you add those all together, it's 3, 6, 10, and then also 6. So it's 16, which is larger than 12, and so it's abundant. And then with 9, the only proper divisors are 1 and 3. And so you add those proper divisors together, and you get 4, which of course is less than 9. And you can test that with 28. I'm not going to go over that. So now we're going to declare integer n, and then we're going to input it from the input stream. And then we're going to declare a vector of integers, and we're going to name it proper divisors. And in this, we're going to, of course, store all the proper divisors of the number. And then what we'll do is we'll iterate through all the items in the proper divisors, add them together to this integer sum of divisors, and if sum of divisors is larger than the input, then we output abundant. If it's equal to, it's perfect, and if it's less than, it's deficient. So let's just go over this for loop and how it works. So we go from 1 to the square root of the number. I discussed this in the previous video, but I'll go over it again. So the factors of a number, of course, exist in pairs. So with 100 would be 1 and 100. I'm not going to go over all of them, but you can see what happens here. And then after it reaches the square root of the number, it flips over. And so it would become 25 and then back to, or down to 101. So all we need to do is cycle from 1 to the square root of the number, and then check if the number is divisible by I, in which case we add I. So let's just say this is I here. We add that number, and then we also add n divided by I. So 100 divided by 2 gives us the second factor. So we only need one number from the pair of factors to determine the other factor. But of course, we don't want to include, let me just erase this here. We don't want to include the number itself. So when I is equal to 1, we don't want to include n divided by I if it's equal to n. Does that make sense? I hope so. Anyways, and also we want to make sure that if the number is a perfect square, that when we reach the square root of the number and we divide the number by that the square root of the number, we want to make sure that we don't get the square root of the number again, because then we would be adding two of the same factors to the proper divisors, and we would be by mistake adding an extra factor, which of course would give us the incorrect answer. So what we're going to do is we're going to check that n mod I is equal to 0, as in n is divisible by I, in which case we add I to the proper divisors. And then here we're going to check that n divided by I is not equal to I. So this was this case here where both of the numbers are the square root of the number. This is only for perfect squares that we are concerned about this. And we also check that n divided by I is not equal to n. So this is when I is equal to 1, because 100 or any number divided by 1 gives the number itself. And we don't want to add the number itself to the proper divisors. And if none of these are, well, if both of these are evaluated true, then we add n divided by I. So like I said, let's just say I is 2, we divide 100 by 2 and we get the second factor in the pair, which is 50. And so in this way we can determine the divisors of a number in O of log n times, so we don't have to cycle all the way to the number to determine the divisors. I hope that makes sense. And then we're just going to initialize sum of divisors to 0. We're going to iterate through all the items in proper divisors. You can use this syntax as a shorthand to cycle through a vector, and I believe it also works for arrays. Yeah, I'm not entirely sure. And then we just add the value of x to the sum of divisors. X is just each item inside of proper divisors. And then, yeah, I already explained this earlier. I'm not going to go over it again. So let's test a couple of test cases. 12 should give us abundant, 9 should give us deficient, and then 28 should give us perfect. Yeah, so that works fine. And let's just also test this largest test case over here, which is 945. Oops. And it gives us abundant. Alright, so that's it for this Olympiad. Yeah, thanks for watching, and I'll see you in the next one.